We are going to be studying nuclear chemistry, which is a completely different branch of chemistry than what I would refer to as ordinary chemistry. So in nuclear chemistry, reactions happen inside the nucleus only, and remember the nucleus has the protons and neutrons in it. Most of ordinary tabletop chemistry or chemistry that occurs in our body, or the oxidation of metals, for example, that type of chemistry that we've dealt with up to this point usually deals with just the electrons that are outside of the nucleus. So nuclear chemistry or a nuclear reaction would occur inside of a nucleus that was unstable. Or we might say it had high energy. And high energy, remember, means the species is unhappy or unstable. And we'll look later on as what the criteria is for a nucleus having higher energy. Some of the nuclear reactions that we'll be looking at, for example, would be neutrons inside the nucleus could turn into protons, or protons could turn into neutrons. And so the particles inside the nucleus we refer to as this vocabulary word, a nucleon. A heavier nucleus like uranium could emit an alpha particle. So that alpha particle is actually 2 protons and 2 neutrons. And also somewhat heavier elements, because of the charge of the nucleus being so high, that positive charge can attract an orbiting electron, and I think of this as the Pac-Man game, but the nucleus itself can kind of gobble up an electron. And in that case, a proton plus the gobbled up electron turns into a neutron. So we will identify each one of those specific types of radioactive decay. So any nucleus that is unstable and stabilizes itself by one of these processes is called a radionuclide. And a radioisotope is the whole atom. So most of this chapter, we are not even going to be concerned about the atom itself and the atom's electrons. We're only going to be concerned about the nucleus inside of each atom. And if a nucleus is unstable or has too much energy, that nucleus will decay spontaneously and emit very high energy gamma radiation. And the Greek symbol for the letter gamma is this letter, which I'll erase that part. So that's the symbol for gamma. And if you recall from looking at the entire electromagnetic spectrum, radio waves are on one side of the spectrum. So these are low energy, long wavelength, and low energy means low frequency. So radio waves are not dangerous. Gamma rays are on the other side of the electromagnetic spectrum. They're very high energy because of the high frequency values and very short wavelength. And then remember, visible light is somewhere in between here. So radiation that is higher in energy than visible light, including ultraviolet, X-rays, and gamma rays. Those are very dangerous. And radiation that occurs at lower energies than visible light, infrared, microwaves, and radio waves, that type of electromagnetic radiation, because it's low energy, is not dangerous. So this gamma radiation, this is what kills people when bombs go off, or if a nuclear power plant goes crazy and the nuclear reactions are no longer contained, then this gamma radiation could escape into the environment. The sun puts off all of this energy because our sun is actually taking 4 atoms of hydrogen 1, which is a hydrogen atom with 1 proton in the nucleus, and converting that to helium. And helium has 2 protons and 2 neutrons. So we're going to be taking a look at just the ordinary isotopes that we may have learned in a previous chapter, and then we'll tailor that to a particle designation that we're going to use for nuclear chemistry. So 2 common examples of just normal isotopes. 2 of the 4 isotopes of carbon I've listed here. So carbon 12 would be an atom of carbon with inside its nucleus 6 protons and 6 neutrons. And then if we're talking about the entire atom, this is a rough drawing, but 6 electrons would be orbiting that nucleus. So the top number, if we're talking about a specific isotope, this number has to be part of the symbol. So the mass number, we call that, I'll put that over here. The mass number here is always the protons plus the neutrons. And protons and neutrons weigh approximately the same thing. So we'll deal with that later. Neutrons are just a little bit heavier. And the number at the bottom of the isotope symbol is always the atomic number. So if we look at carbon on the periodic table, what makes an atom of carbon have the identity of carbon is the number of protons. So the atomic number is the number of protons. So we would refer to that as the atomic number. But again, the atomic number is the protons. Let me erase this. So in earlier classes, all we may have cared about, let me put an arrow towards that. In earlier classes, we just wanted to learn the representation of a particular isotope. And from that representation, if we subtract the number of protons from the protons and neutrons, the difference is actually the number of neutrons. So, and also, if we look at the mass number on the periodic table, this mass is generally used most often just to convert from grams to moles and so forth. But remember, that number is a weighted average of all of the isotopes according to their relative abundance. So many times we can just look at the periodic table and tell the difference between the atomic number and the average mass. We can tell which isotope is the most abundant. So carbon 12 weighs exactly 12 AMUs, but the weighted average of all the isotopes of carbon is still very close to 12. So we could do that for nitrogen. Nitrogen has 7 protons. Since the weighted average of all the isotopes is 14, we would say, well, we could take a very good guess that the most abundant isotope of nitrogen would be nitrogen 14. So not every atom or nucleus is radioactive, because that would probably mean the end of the human population. But every atom has a variety of isotopes, and those isotopes that are unstable are going to decay spontaneously. Even if we cool that atom down to absolute 0 degrees Kelvin, that nucleus will still decay spontaneously If we react the radioactive atom with another element to form something new, the nucleus is still going to decay radioactively. So that is something that there is no way to stop that process from happening. So what we do generally is we learn how to protect ourselves from that. And looking back at the electromagnetic spectrum, our atmosphere blocks off most of this very high energy radiation. So we're pretty much safe just walking around. Now what we're going to do when we talk about a symbol for a nuclear particle, it's going to have the same format. So a nuclear isotope symbol, I'm going to write with an X. So if we write X here, the top number is still the mass number. So the mass number is always the protons plus the neutrons. And the bottom number is still the atomic number, but we're going to call that number the charge. So if we look back at either one of these isotopes of carbon, carbon has 6 protons in the nucleus. So if the nucleus does not have 6 protons, then that atom is not carbon. So 6 protons means this really has a charge of plus 6. The nucleus has a charge of plus 6. Because neutrons are neutral, they are not going to affect the charge. So our symbols, whether they are nucleons, meaning radionuclides, whether they're a nucleus, or whether they are one of the emitted particles that are given off during a reaction that is radioactive, we're going to see a number at the top and a number at the bottom. And if we have a particle that's emitted, for example, an alpha particle, since an alpha particle, we'll define all these in just a few minutes. Since an alpha particle has 2 protons and 2 neutrons, then the charge would be plus 2 and the mass number would be 4. And just like any equation, the equation has to be balanced. So whatever our unknown nucleus is, because when a nucleus undergoes radioactive decay, it actually becomes a new atom. For example, carbon-14 is radioactive. We'll see later that it's unstable because the protons and the neutrons are quite different. Carbon-12 is very stable. So up to atom number 20, which is calcium, a nucleus likes to have approximately the same number of protons and neutrons in order to be happy. So carbon-12 will not decay radioactively. This isotope is stable. But carbon-14, because of the excess neutrons that are present in the nucleus, this one is radioactive. It's used for carbon dating. And when carbon-14 decays, it actually turns into nitrogen. So the process of nuclear decay results in a new atom or a new nucleus. So if we keep in mind that the arrow is like an equal sign, then whatever the charges are across the bottom, so on either side, the charges must balance on both sides of the equal sign. And also the mass number across the top has to balance. So I didn't give us a mass number here, but we will do some examples for that. So if we learn the 4 types of radioactive decay, this one being alpha emission, if a problem gives us a particular nucleus, that problem will give us the mass number and its charge. And if we're told that it decays by alpha emission, then we just have to figure out what this number is, what number plus 2 equals the number that was given, and then that number will identify what atom we're talking about, and then what isotope of that atom is depends on what number, when we add 4 to that number, equals the number that was given in the problem. So it's not a difficult concept if we keep in mind that everything on both sides of the equation must balance. On the next video, I'm going to actually list the types of nuclear decay that we're going to be considering, and we'll see what's really happening during that process. Is a neutron turning into a proton, or is a proton turning into a neutron? And so we'll see particles that result, beta particles, alpha particles, positrons, and so we will be looking at that shortly.